All right. Good morning. Survived that nice cold weather yesterday. All right. So, any questions on all the review that I did last week and the preparation for experiment 30? Everybody good on that?
Start over from the beginning.
No. Watch the video. You have a quick question, I'll answer. All right. So today, we move on to a new type of transistor. Junction field effect transistor. From here on out, I usually just say JFET because it's easier. So what differs here is the general construction of it. The concept of the semiconductors and everything that we've already done before, we're just going to reiterate, we're just going to put it together in a different way. So the first idea here, all right, is I'm just going to start with just a general concept of a large block of N-type material. Now, this N-type material, right, has been doped. It has free electrons in it. And so it will conduct current. It actually almost acts more like a resistance. Yeah, I mean, that's how resistors are made, right? They're made out of carbon. Carbon is a semiconductor material. So I've added enough impurities to this to make it conductive. And just for the sake of argument, let's say that it has, if I were to hook this up to a voltage source, I'll go ahead and put a resistor in here, as we always tend to do, just as a means of providing. Actually, you know what? I don't need a resistor in this one. I already have a resistor. This is my resistor. So we'll just go ahead and hook up a voltage source. I'm going to make it variable for later purposes. But for now, if this just acts like, again, for argument's sake, we'll just say it's 100 ohms of resistance. Now, pretend that I would have access to the entire length of this device. If I were to take a meter, let's say I go ahead and I set my variable voltage here to 10 volts. If I were to take a meter, we'll go ahead and use this as our reference point, just for sake of argument there. So I go to measure the voltage with respect to ground. If I were to hook it up right here, what would I read? What am I going to read? Zeros. If I were to hook it up all the way over here, what would I read? 10 volts. And if I could say sticking about in the middle, what would I read there? 5. Think of this resistor as just like a variable resistor, right? Continuous amount of resistance all the way, which means the voltage is going to be divided pretty consistently. Make sense to everyone? Okay. Now, the next thing I'm going to do is we're going to dope this to create P-type material. Now, the P-type material is going to be along the edges. I'm kind of drawing this as a dashed line because when I do that, I will create a junction. So this is P-type material. And even though I'm not going to show it on here, just imagine they're connected together. All right, electrically, they're connected. So initially, I'm going to hook this P-type material up to ground, which of course makes all of the P-type material with respect to ground 0 volts. Now, let me go ahead and name, we've made 3 connections to it, right? We made a connection on this end, we made a connection on this end of the channel, and we made a connection here. 3 connections, 3 terminals. The P-type material here, connection, this is the gate. Down here, where I've connected my negative voltage, my reference, if you want to call it that, this is the source. Down here on the positive side, this is my drain. Now again, up to this point, the only thing we've worked with is bipolar junction transistor. Anybody see the similarities in a couple of these words? What does the source do, potentially? Yeah, it will emit things. Emitter. What does a drain do? Collects things. There's your collector equivalent. Means the gate is going to be simply the equivalent to the base. Exactly. Make sense to everyone? All right. Now, in general, if this is a resistor, which as it was set up initially, before I put the gate on there, it was a resistance. How does a resistance respond to changes in voltage? As the voltage goes up, the current goes up. All right. So here's what we're going to do. We'll draw a graph here. Call this our drain current. And the voltage between the drain and the source is the voltage we're going to measure, right? Basically, the supply. Now, technically, this would be called a drain supply voltage, right? Same thing we use the collector supply voltage, VCC, VBB, base supply voltage. But because they are connected directly to the drain and the source, whatever we have here will be the drain source voltage. So we'll make a graph here of the drain current versus the drain source voltage. So initially this is just a resistor. And as this voltage goes up, the current goes up. But let's see what else is happening. Let's go ahead and make this, we'll start with 1 volt here. So if this is 1 volt, at this point, 0 here, what would be the voltage roughly in the middle? Half, right? Half of 1. Well, let's go all the way this end where it's 1 volt. This voltage is applied to what we call the channel here, the N-type material. What is the voltage on the gate? 0. So that actually means that the P-type material is at 0 volts. The N-type material here is 1 volt. What am I doing to this junction? If the N-type material is more positive than the P-type, that is reverse bias. What's happening? Well, if I look at this as the junction, what happens when I reverse bias a PN junction? The depletion region grows. And so what I'm doing is I'm basically kind of creating a little bit larger depletion region to the point where I get down here where it's 0 and 0, there's no difference. So with 1 volt applied, and as I get closer to the 0 voltage, I'm trying to make this get smaller and smaller. I'm actually taking the channel and starting to narrow it. But back here, where it's still 0, I am basically getting electrons moving, and they will keep moving. So as the voltage goes up, it's still acting like a resistor. As the voltage gets higher, right? So if we go up to 2 volts, okay, now that depletion region is twice as big. But again, back here, I get the electrons moving. Electrons will move through a depletion region if I've already got them moving. But eventually, and we'll go ahead and go with 3 volts here. Let's say at 3 volts now, we actually create a point where those depletion regions meet. Now, what happens at that point with my curve is that until then, as I increased the voltage, the current rose. But once I get to what we call that pinch-off point, the increasing current stops increasing. I reach essentially saturation, right? Not saturation, not the best word. I reach a maximum amount of current flow. Remember, this curve was for when the gate to source voltage was 0. That maximum current is referred to as IDSS. It's the drain to source saturation current. That's why that saturation word came in there, even though the regions are a little bit different. That is the maximum amount of current that this device can ever have. Now, let's make things more interesting. I'm going to get rid of all this. Right? So you saw what happened as I increased that voltage. Now what I'm going to do is I'm going to add another supply in here. So this is my gate supply voltage, which, because there's no resistors involved, is going to be applied directly to the gate. And notice the polarity, right? Negative, positive. I'm applying a negative voltage to the P-type material. So now, even before, so this started off at 0, right? And then we went up. So even before I apply any voltage to the drain, the P-type material is going to be more negative than the N-type material. So I start with a reverse bias junction all the way across. So even before I do anything with the drain voltage, I am starting with all the way a narrower channel. So by starting with that narrow channel, what is the resistance of this material going to be? before, when the drain voltage was going up, I was only narrowing it down here. It was still fully open down here. But now, starting, and we'll assume this is 1 volt for now. All right, so we got a negative 1 volt applied to that gate. The whole channel being smaller, what's going to happen to the resistance of this block? Go all the way back to 113. Think of your formula for the resistance of a wire, proportional to length, and inversely proportional to area. So if I am narrowing that channel, that means the resistance of that channel is going up. So now as I start to raise this drain voltage and draw current, pull those electrons down there, make current flow, because the resistance is higher, for a given amount of voltage, the actual current I get is a little bit less. In other words, this line is not as steep because it's current versus voltage, it's inversely proportional to resistance. So higher resistance results in less slope. More importantly, when this gets up to 1 volt, I now have 2 volts of reverse bias on this end. Okay, so when I get up to the 2 volts, I'm sorry, with 1 volt there, with 1 volt, now I'm narrower here, all right? And then the narrowing of it reduces back here. So just like before, we continue to increase, but what does it take to pinch this off? Before, that happened at about 3 volts. In fact, if I go ahead and draw this line here, right, let's call that my pinch off. This is called the pinch off voltage. In my example earlier, it took 3 volts to do that.
The maximum current is less.
Okay, so 2 things are happening here, right? We're starting off getting less current for the voltage, and because this pinches off with 3 volts, I've already got 1 volt reverse bias there, which means this, once this gets to 2 volts, I reach that maximum current flow. Go around, and we'll just kind of draw that there, right? Right around there, we reach that maximum current a little bit sooner, right? So now, this, of course, is a gate source voltage of -1. What's next? Oh, now let's increase this to 2 volts. So when I start off with -2 volts, I'm starting off with a much narrower channel, higher resistance. And so the slope is lower because of that higher resistance. And what's this got to get to before I start to get that pinch off point? 1 volt. Now I have 1 minus a -2, that's 3. And so with only 1 volt here, now we pinch off up here, right? And then we've got the smaller channel there. So I very quickly reach that maximum. Then finally, what happens when I increase this to 3 volts?
Nothing.
No channel, no current flow. Okay, so I'll pretty much immediately just get my depletion region right there. It's one big depleted block, no current flow. Go ahead and put that here. I'll just flat line there, right? So there's your gate source of -. Make sense to everyone? So what does that look like? What do those curves look like? A little bit. Is that? They look a little bit like the curves that we had for a bipolar junction transistor, right? We had collector current versus collector emitter voltage. Then we had lines that looked a lot like that, but they changed based on the base current, whereas these lines each are differentiated by the gate source voltage. So we will be able to use this device in a very similar manner to what we were able to do with a gate source. I'm sorry, a bipolar junction transistor. With some differences. Numbers are going to be a little bit different. Now, some of the terms here, all right, that we're going to be using. So down here, that's going to be cutoff. Like a regular transistor, right? You don't provide any base current, you get no collector current. Here, you get a high enough gate source voltage, negative gate source voltage. You get no drain current. Now, over here, this region is a little bit different, right? In a bipolar junction transistor, we call it saturation. Here, we're going to call it the ohmic region. Why that? Well, what does it act like here? It acts like a resistor. It acts like a resistor. And then we'll still call this the active region. And I'm not going to draw it in here, but just like any depleted region, if the drain source voltage gets high enough, I can cause breakdown and cause excess current flow. I don't call that an operating region, so I don't necessarily want to draw it. But understand there are limits to voltages for the same reason. All right?
Here, you've been talking about VGG. That's, in this case, always equal to VGS, right?
In this example, yes. Because I'm providing a set gate volt or a set voltage to the gate with respect to source. Yeah, when we start biasing this,
Resistors.
we'll put in resistors and it won't be as, it'll be different. Yeah, exactly. And we're going to, similar to what we did with our bipolar junction transistors, when we start biasing this, we're going to have a number of different ways to bias it, and we're going to make our analysis based on some assumptions. So we'll go from there. But these assumptions are even easier than, or not easier, but even more of an assumption, I guess, than we did with our bipolar junction transistor. All right, so notice that in this example, right, for this transistor that I built here, the gate source voltage at which there is no drain current was -3 volts, which was also corresponding to, in my example for this curve with the gate source voltage equal to 0, that pinch-off voltage was also 3 volts, right? That's what it takes for that to happen. So a couple formulas we can use here, all right? The gate source cutoff voltage, that's what this ended up being, is equal to the negative of that pinch-off voltage. Addition, for this particular curve right here, because it's acting like a resistor up to that point and that point, this is referred to as the drain source resistance, RDS. I don't remember if you had an additional subscript on there. I don't think he did. Double check here. Nope. Okay. So the drain source resistance, and I'll put a caveat on here in a second, is basically going to be voltage divided by the current, which would be the pinch-off voltage, divided by IDSS. And I'm going to just put this at a gate source voltage of 0. Because if I change the gate source voltage, the slope of this curve changes. And therefore the resistance of the transistor changes. We're going to actually use that concept as one of the applications that a JFET can have. In a little bit. So one of the ways we're going to, as we study this transistor and we start to use it and make our approximations. So when it's in cutoff, what assumption can we make? So if we're in cutoff, the assumption we can make is that the drain current, 0. If we're in the ohmic region, we treat the transistor like a resistor with this resistance, RDS. Now, what about when it's in the active region? How are we going to know this, right? How are we going to look at this? Is there a formula we can use to kind of determine what the drain current will be based on the gate source voltage? Is there a relationship here? Short answer is yes, there is. It's going to be a little bit different than what we've seen before. First off, we can see that the maximum occurs when the gate source voltage is actually 0. The minimum occurs when the gate source voltage equals the gate source cutoff voltage. Here it is. I had it written down. Okay. So it's like inverse relationship. In addition to which, you'll notice that a 1 volt change in the gate source voltage creates a lot lower or big drop in current there. Not as big there, not as big there. Which means the relationship, in addition to being inverse, is also non-linear. Now, I'm not going to try, I've never seen this derived anywhere, or if I have, it's been too long to care about. Okay. But this transistor actually obeys what is known as the square law effect. So here is the formula for this. The drain current, this is in my active region. The drain current will be drain saturation current, IDSS, times 1 minus, right? So that minus, that's my inversely proportional. The gate source voltage divided by the gate source cutoff voltage, quantity squared. That's the square law part. Let's do the math real quick, right? So if the gate source voltage is 0, well, 0 divided by anything is 0. 1 minus 0 is 1. 1 squared is 1. And therefore, the drain current will be IDSS. Go to the other end here. The gate source voltage equals the gate source cutoff voltage. Then anything divided by itself is 1. 1 minus 1 is 0. 0 squared is still 0, and the drain current will be 0. That's pretty precise, right? That's almost as good as my bipolar junction transistor, where I got to say, hey, I can calculate the base current. You just multiply that by beta, there's your collector current. What's the problem with that, though? For my bipolar junction transistors, beta was not a constant. It changed temperature, transistor to transistor. It even changed depending on how much collector current there was. So the problem here, as precise as this is, the potential range of my drain source saturation current and the range of my gate source cutoff voltage make this formula not as good to work with. I can't just plug it in and say, here it is. Because there's too much variability between transistors in particular. And we'll show you the spec sheet here in a little bit to clarify that. All right. Got a question, Hugo? All right. That's the gate source cutoff voltage. That was what we defined as the negative of the pinch-off voltage.
Where the variability is between different devices at that DGS top.
IDSS as well. Yeah, both of them. And so when you make this one variable and you make this one variable, this formula could just be almost anywhere. But it's still worth looking at because it does tell us what the relationship is. And therefore, if I change something, like insert a small change in the gate source voltage by, I don't know, applying a sinusoidal waveform to it, then I can predict how it will react. Kind of an AC model.
What would happen if you plug the VGG source?
If I reverse that, well, the way this is built right now, there is no resistor to limit the current, because if I reverse this, what do I do to the junction now? I forward bias it. And what happens then? Current flows. And if I don't have a resistor to limit the current flow, you'll damage it. So usually I think for your labs, you do put a resistor in. But think about it. The size of the resistor. Remember how with gates, when we had our bipolar junction transistor and we wanted to do voltage divider bias, we couldn't use too big of resistors because it did have to supply base current. And so that became a load on my voltage divider. And if you want a stiff voltage divider, you want to make sure that that voltage doesn't change very much. When I bias this gate, how much current do I have flowing? Pretty much nothing, right? It's a reverse bias junction. Which makes it, I'm getting ahead of myself here, but it makes its input impedance what? Also very, very high. So a little bit different, right? A little bit different than my bipolar junction transistor. But I have these curves and I have these relationships that I can still use to figure out what's going to happen. And you can actually, if you were to graph this formula right here. Okay, squeeze it in here. Well, actually, notice how the curve's going this way, right? Because if this is my gate source voltage, that's the negative direction. And this is your drain current. Then what you have is with 0 gate source voltage, you have IDSS. The gate source voltage reaches the gate source cutoff voltage. The drain current reaches 0. And then the shape of this curve is basically a x squared function, right? So as you start off at 0, like that, and then increases. So keep in mind that mathematically, once I get the gate source voltage greater in magnitude than the gate source cutoff voltage, then this just becomes 0. Right? Working back way here, this will always be 0 from there on out. So that this formula only applies in this region here, which is that active region. Make sense? All right. This, by the way, is known as the transconductance curve. So conductance, right? You usually think of conductance. You recall what conductance is. It is current divided by voltage, right? The opposite of resistance. And what we're doing essentially is a voltage is going in and a current is coming out. And so what you're doing is essentially taking that voltage divided by a resistance to create a current, or you're multiplying by conductance, which is why this is called a transconductance curve, like a transfer from the input to the output. Shows me that relationship between voltage coming in and the current that results. All right. I filled that one up pretty well. Okay. Now, let us talk about biasing in the ohmic region.
That's in the active region.
The transconductance curve, that is for the active region, correct.
Well, here you could apply a signal to between the gate and the source. BGS,
Which one are you looking at?
transconductor.
Yeah, that's gate source voltage, that's gate source cutoff voltage right there. And so and we're going to get to that.
Vary the current coming out.
Right. So by varying the gate source voltage, I will vary the drain current.
So if you have a load resistor, then you can be varying the output voltage.
And that is how we will create an amplifier using this in a couple more sections. So initially, I thought I had a spec sheet in here, but I'm not finding it. Oh, there it is. Figured the easiest way to do this. Before we start about the bias in the ohmic region here, I just want to go ahead and talk about the spec sheet a little bit. So when we start using these numbers, we kind of see what we're looking at. today. Skip. Multiple ways around this here. All right, so this is a spec sheet for the MPF 102, a JFET amplifier. This is actually the transistor you're going to get next week with your kit that you're going to be doing your labs with. Now, take a look at some of the numbers here. So you got your maximum ratings, right? Remember I said there's a maximum drain source voltage rating, 25 volts. You don't want to go above that. If you do, you have that potential to break it down, and now you have no control. Other maximum ratings. Here's what I want to look at. We'll start with our off characteristics. Specifically, the gate source cutoff voltage. It doesn't even provide me with a minimum. It doesn't even give a number. The maximum, -8. So technically, what is that? That's a range from anywhere from 0 to -8. Not very good. Now, historically, I will tell you, for your transistors, it's usually about -1.5, roughly, all right, based on labs. Okay, so not very helpful to me. Now, on characteristics. So this is my IDSS, the zero gate voltage drain current. Minimum 2 milliamps, maximum 20. That is a factor of 10 for my range for IDSS. Again, too big to really use these formulas directly and just say, oh, we can just plug it in and figure out exactly what it's going to be. Too much variability. All right, so those are the main things that I wanted to point out there. It's just a huge range from 2 to 20 for IDSS. If you want to just use this, I don't know, -0.5 to -7.5. That's still a huge range. That's a factor of 15. So you got 15 times 10, that's 150 variable. That's 2 orders of magnitude, 2 powers of 10, over 100. So we just cannot use that formula directly. But again, what we will eventually use is the concept of it, right? What it looks like. All right, so biasing in the ohmic region. Let me go ahead and redraw a curve. When I'm biasing in the ohmic region, what I want to do is focus on that first curve. What I'm trying to do, biasing in the ohmic region, is I'm trying to make the transistor as conductive as possible. That means minimum resistance. When does that occur? That occurs when the gate source voltage is 0. So we're going to focus on that one curve where the gate source voltage equal to 0. One of the problems, of course, this is IDSS. So what I need to do to basically make sure that I'm in the ohmic region. Oh, you know what? I never drew you the schematic symbol for my JFET, did I? Let me do that here real quick. There's your gate, drain, and source. This is an N channel. Try to redraw that, change everything to where the N-type material starts off as P-type. My gate material now becomes N-type. That would be a P channel JFET. And all I have to do to differentiate that is point the arrow the other way. So both types are available, N channel and P channel.
What does the SS stand for in IDSS?
Drain current with a shorted gate. Shorted gate. IDSS. So basically that's when the gate source voltage is 0. So the gate is shorted to the source. That's essentially what that means. I was looking at this earlier and I can't remember exactly because I know it's not the best term, and if you saw from the spec sheet there, right? On the spec sheet they called it zero gate voltage drain current. Okay, and they labeled it IDSS. The text he calls it shorted gate condition. Never really gives it a better name than that. So I don't have a great name for you. And that's why I usually just say IDSS.
That's max abbreviation.
Because IDSS stands for current drain to source with shorted gate.
Okay, where'd you find that? I missed that.
Page 421, top paragraph. The paragraph right above the ohmic region.
Oh, okay, I see. All right. He didn't have, you know what, I was looking for italics. He didn't italicize it. Other than IDSS, yeah. Current drain to source with shorted gate. So there you go. All right. So current drain to source with shorted gate. So there's your IDSS. Again, IDSS is just easier to say. Kind of like our prime E, right? With our bipolar junction transistor. Just easy. All right. So when I build a circuit, to bias myself in the ohmic region, I'm going to have a drain resistor, a drain source voltage, my transistor, source connected to ground, and the gate connected to ground. So this guarantees, so I could draw like that, or I think the book might draw it like this, right? Put a resistor in if you want. But anyway, however you look at it, the gate is connected to ground. This would be your gate resistor if you have one. Now, that guarantees the gate source voltage is 0. The only way that I can guarantee that I'm on this part of the curve is to make sure that the drain saturation current is much less than IDSS. Now, what is the drain saturation current, right? That is the maximum amount of current that could occur if the drain was shorted to the source. In other words, if this transistor acted like a dead short, which basically puts the entire drain supply voltage across the drain resistor. And that's how we calculate it. The drain saturation current will be the drain source voltage divided by the drain resistance. Should look familiar, right? It's the exact same way we found the collector saturation current, except it was collector supply voltage and my collector resistor. Sense to everyone? What is that going to do? Well, if you were to look at for the circuit here, this, of course, is my drain voltage. Drain voltage will be equal to whatever the drain supply voltage is, minus, right, it's going to create a voltage drop there. This is my drain current. It'll just be the drain current times the drain resistance. That's what creates that voltage drop. Subtract that from the drain supply voltage, gives me the drain voltage. Now, what would that curve look like? Well, that curve would be the drain, maximum drain source voltage would be if the drain current was 0. That would be the drain supply voltage. As the drain current goes up, right, starts off at 0 here, as it goes up, the drain voltage, as I'm subtracting a large number from a set number, will go down. That is what we call the characteristic curve of this circuit. This is what we get when we have a fixed voltage flowing through a resistance. And of course, this current right here would be when the drain source voltage is 0, and thus when that's 0, those two are equal, and that gives me my drain saturation current. And so as long as this is well below IDSS, that intersection will occur in the ohmic region. And as long as you're in the ohmic region, what is this transistor acting like? It is acting like a resistor, and so I can redraw this circuit There's your drain resistor. Replace the transistor with a resistor. And of course, the resistance is the RDS that we calculated earlier. Just a reminder, that's the pinch-off voltage divided by IDSS. This, of course, is my drain. And thus, my drain voltage would be right there, which could also be calculated by taking the drain current and just multiplying it by this. That's all it is. It's exactly right. It's a voltage divider. In terms of analyzing the circuit, that's all we have to do, right? Throw some numbers in here. You know, using my example earlier, let's say that IDSS was 10 milliamps, and my gate source cutoff voltage is negative 3 volts. That, of course, means that the pinch-off voltage is 3 volts. Therefore, RDS would be 3 volts divided by 10 milliamps, which would be 300 ohms. Then for our analysis, let's say my drain supply voltage is 20 volts. Now, this is the tricky part right here, right? This author usually defines much less than as at least a factor of 10. So if we make our drain resistance here, let's say our drain resistor is 20K, then our drain saturation current would be 20 volts divided by 20K, or 1 milliamp, which is 1/10 of my IDSS. So I meet that condition. Now, part of that is just that large range of IDSS. Right? How do we make absolutely sure that we're in the ohmic region? That'll do it. So under these conditions, we are in the ohmic region, which means our drain resistor is 20K. We just calculated our RDS as 300 ohms. Then the drain voltage would be, again, it is a voltage divider, so we could just use our voltage divider formula, right? 20 volts being divided. We're looking for the drain voltage, which means it's the voltage across RDS, so that'll be 300 divided by the total resistance, which will be 20,000 plus 300, which is 20,300. Calculator here. All right. So 20 times 300 divided by 20,300 gives me 0.296 volts. It is very small, which is exactly what we're going for here, right? The goal of operating in the ohmic region is to maximize the current flow. The only way we do that is to minimize the resistance as best we can, which is going to be a minimal amount of voltage. Make sense to everyone? Yes, sir.
20 volts in the
I gave the drain supply voltage as 20 volts.
oh,
I had two different things. I didn't write everything on it. I forgot to write there. Which is where I should have started, because that was my original circuit. The bottom line is I gave it to you. Okay. Not an assumption you have to make. You will be given the information you need to figure out what is the drain saturation current. If I meet the conditions, I can treat it like a resistor, and then I can calculate what that resistance would be. Finish. All right, good. That's biasing in the ohmic region. Next up, biasing in the active region. Now, there are a number of different ways we're going to do this. We'll go ahead and get started, at least one of them here before we take a break. The applications for the JFET, we're going to get to here, some of it today, and some of it will probably have to wait till next week. But think of it a lot as a bipolar junction transistor. Okay? If I am operating in the active region, I can use that relationship between the gate source voltage and the drain current to build an amplifier. Same thing we did with a bipolar junction transistor. With a bipolar junction transistor, we had a cutoff region, just like we do here, right? We still have cutoff. And what do we call the other region? What do we call the area here on a bipolar junction transistor? It was saturation, all right? Characterized by a very low voltage across the transistor. A very low voltage across the transistor. What are we trying to do? Between ohmic and cutoff region is the same thing that I would do with a bipolar junction transistor between saturation and cutoff. And that is used a transistor as what? When it's on or off, we're using the transistor as a switch. We can do similar things here. But we can even be a little more creative, because it's not just a low voltage in that ohmic region, it's also a resistor. We'll play a little bit around with that. So we have more options available to us than just on and off. All right. So biasing in the active region. So with the active region, we are going to use another resistor. I have a gate resistor, but that gate is still connected where? The gate is still connected to ground. But the source, unlike my ohmic bias or my bias in the ohmic region, the source is not connected to ground now. There's a source resistor here. And then I have my drain resistor. So this is where the transconductance curve, I'm going to make a little bigger one here. I'm going to illustrate. So what we have here, this is called self-bias. When we look at the gate source voltage, gate voltage here, of course, 0. The source voltage is right here. What will that be? Well, in this circuit, we're looking at some drain current. And of course, we have source current here. In our bipolar junction transistor, we had collector current, we had emitter current. And we generally theorized, or we generally assumed that those two currents were what? Equal, because the base current was so small. What's true here? You look at this as a junction here. What kind of gate current do I have? Well, for a reverse bias junction, it might as well be 0, which means the source current and the drain current here will also be equal. In fact, in some ways, they'll be more equal than they were with a bipolar junction transistor. Which means that the source voltage here will be whatever the drain current is times the source resistor. The gate source voltage, using a common reference point, is the gate voltage minus the source voltage. Well, we've already determined the gate voltage is 0, so the gate source voltage will be negative the source voltage, which is negative drain current times source resistance. So when the drain current is 0, the source voltage will be 0, and so the gate source voltage will be 0. So you actually start off right here. But as the drain current goes up, that creates a voltage across the source resistor, which now makes the source more positive than the gate, or the gate more negative than the source. So as the drain current goes up, so does that negative gate source voltage. When you get an operating point. That operating point is going to be in that active region, guaranteed. Now, this assumes a certain value of source resistance. If we were to make the source resistor larger, right? So if I just say Let's call this RS here, all right? If I were to make the source resistor larger, then for a given amount of current, I get more voltage. So this would be a larger source resistor. And then contrary to that, what? Smaller would just mean less voltage for the amount of current. Depending on the size of the source resistor, kind of determines roughly where you're going to be operating. And the beauty of this is, remember how this curve, I fixed an IDSS, I fixed the gate source cutoff voltage. This curve could literally be anywhere. But no matter where it is, what I'm going to do, I will intersect it at some point. And I will bias in the active region. Can't be real sure where exactly, but hey, I'll be in the active region. So he usually recommends, or the author says that the preferred or recommended, I'll just call it recommended, source resistor should be about whatever RDS is. So my example earlier, we had 300 ohms. So, 330 ohm resistor. Well, close enough. So that is self-bias. And there are other types of bias, which we will go ahead and cover after a 10-minute break. So we'll go ahead and take 10 minutes. We'll come back at 5 till the hour. And we'll look at some of the other ways to bias this transistor. All right, so that was self-bias. Next type of bias we're going to look at should be familiar to you. That is voltage divider bias. Well, very similar to self-bias in that I'm going to have a drain resistor, a transistor, a source resistor, and lo and behold, a voltage divider. But what is this going to do? I will set a gate voltage with respect to ground, just like our voltage divider bias for a bipolar junction transistor. It'll be the source voltage times R2 divided by R1 plus R2. How does that change this formula? Well, what it does is because the gate voltage is no longer zero, it is whatever the gate voltage is minus the source voltage, which will once again be drain current times the source resistor. So on my graph, instead of starting out down here at zero, if the drain current is zero, then the gate source voltage would be whatever that gate voltage is. That do. Well, More importantly, when the gate source voltage is zero, right, which is this line right here, gate source voltage zero. When that gate source voltage is zero, that means that the drain current will be equal to, move that to the other side, becomes positive, solve for that, would just be whatever the gate voltage is that I just calculated here, divided by the source resistor. So the curve starts off when the gate source voltage is zero at some current, non-zero. As the current, or as I start to get a gate source voltage, as this goes negative, as the drain current goes up, then I'll get a slight increase in the actual drain current as the gate source voltage becomes negative. So get one intersection point, get an operating point that is in the active region. Difference is basically where I start. And notice that the slope of this line is not real big, which if you recall from the self-bias correspond to a larger resistor. And so that allows me to use a relatively larger resistor than drain source voltage. But because I have the additional starting point, I'll be operating. Now, thing is, to actually solve for the intersection of that point, we can use the formula for this line right here, which we essentially have here, combined with the formula that we have for this curve to solve for where that intersects. Trouble is, right, this curve might look like this. Depending on what your IDSS is. It might look like this, depending on what your gate source cutoff. So there are multiple possibilities, depending on exactly what our curve is. So we're going to make a very broad assumption here. To do these calculations, we are just going to assume that the gate source voltage is zero. Now, how much of an assumption is that? Well, it's not too bad. You know, it gets better the larger the gate voltage is. So if I have, say, 30 volts here and I make this 10 or something like that, well, a few volts there out of 10, not too much of it. So by assuming that the gate source voltage is zero, if we rewrite that formula, then we're basically just saying that, oh yeah, you know that calculation I made earlier? The drain current started off right here, right? That's the drain current at gate source voltage equals zero. We're just going to take that gate voltage, divide by the source resistor, and say, you know, it could be anywhere here, but we're just going to assume that it's right there. It might be a little bit higher. Close enough. Bigger the source resistor is, the less of an issue that is, right? The bigger the source resistor, the flatter that line. So it's not too big a stretch. It's not too big of a stretch. Another option, to supply source bias. So the bipolar junction transistor, we call this two supply emitter bias. Because the idea here or there was, well, you can either make the base more positive than the emitter or make the emitter more negative than the base. Same general idea here. Still going to have the source resistor in. We're going to have our source resistor, but now I'm going to make that negative. This is a negative source supply voltage, ESS. And we can go back and go ahead and make the gate voltage 0 again. So now, instead of making the gate voltage positive, the gate voltage is negative, and so now we make the negative voltage here. So what is that going to do for us? Well, again, the gate voltage is 0. The source voltage is even more complicated now. What would that be? That would basically be whatever the voltage. So if I start from ground, I have minus VSS plus RF. So it would be, in the end, source resistance times the drain current again, minus VSS. With the gate voltage being 0, that means that the gate source voltage would be 0 minus the source voltage. So minus that becomes, right? That negative becomes positive, that becomes negative. And you see a very similar formula to what we had earlier. But just like we did before, right? So again, when the gate source voltage is 0, now the drain current would be whatever VSS is. So at gate source voltage of 0, the drain current would be the source supply voltage divided by the source resistance. So I get a starting point. As drain current flows, that becomes negative. So I get exactly the same type of curve. And thankfully, the same assumption. Because again, it's complicated, right? Depends on where the curve actually ends up. We're just going to say, hey, you know what? That's close enough. So assuming gate source voltage of 0, we end up essentially making the same assumption, except this time, instead of it being the gate voltage, it is now that negative source supply. One more. Well, the other thing that I can do, a little bit unique to this, is actually to go ahead and use my bipolar junction transistor to create a current source. This is called current source bias. Now, because this is an emitter, we'll call it a minus VEE. Oh, missed something. This resistor here. So now, instead of having a source resistor, we're basically putting in its place a bipolar junction transistor with an emitter resistor. The gate is grounded. It's interesting. He doesn't put a resistor on the base circuit, but he does put one on the gate. So fine. Now, this part right here, right? That's a current source. The base emitter voltage drop, which we are quite aware what that is that a lot? 125. And we can calculate here that the emitter current for the transistor would simply be, if you do a Kirchhoff here, you've got minus VBE. There's your emitter current. So minus emitter current times the emitter resistance. And then as I go to ground, plus VEE. That's my loop. That equals 0. Solve for the emitter current. And you basically have the emitter supply voltage minus the base emitter voltage drop. Plus that, minus that. Move that over there, becomes positive. And then divide by the emitter resistor. And because that's the emitter current, that's the collector current, that's the source current, and the drain current, right? All the current running through those two transistors is exactly the same. And there's your drain current. Now, what does that do on my curve? Well, it gives me a starting point. Let's just say it's right here. And then this line is flat because it's a current source. Constant current, no matter what the voltage. And now you have an operating. Questions? See what kind of fun labs you have coming, right? So all that is summarized, table 11-1 on page 437 of the text. So now, of course, that leaves us with, what are we going to do with it? We've got it in the active region. What can I do with it now? I'll go ahead and go with just the general voltage divider bias, just because, it's easy. You should be fairly familiar with it. But what we haven't done yet is essentially create a equivalent circuit. When we did our bipolar junction transistor, we got an AC model associated with it. We can do the same thing here. AC model of a JFET. Now, the one you're most familiar with, one we used a lot, was our pi model. This was, of course, the pi model we used for bipolar junction transistor, where the input resistance was beta times R prime E, the AC resistance of the emitter diode multiplied by beta, the current gain of the transistor. Well, what do we have at the input of a JFET? It is a reverse biased PN junction. So we just identify that as the resistance between the gate and the source, all right? This is not RDS. This is RGS, which is a very, very high resistance. Typically mega ohms. I don't know if he gives a rough number or not. I don't really see one. Okay. Here's your gate. Here's your source. Here's your drain. Well, I'm still modeling this as a current source, right? Because we know what? What do we know? This is my transconductance curve. I'm operating somewhere on this curve. Wherever it is, right? We're biased in the active region. Use our voltage divider bias to get us there. So we are operating at a gate source voltage, DC, and a drain current, DC, right? That's our stable operating point, right? We just call it Q point. So now, if I inject a signal at the gate with respect to the source, right? It's supposed to be a sine wave. Not very good, sorry. What's going to happen? Well, I'm going to move up and down that curve. That will create a change in the drain current. So that change, this would now be what? AC gate source voltage. And then that change in drain current would be my AC drain current. How are those related? Well, this has a formula. Formula for that was, of course, the drain current is equal to IDSS times 1 minus the gate source voltage divided by the gate source cutoff voltage squared. What we're looking for is a small change in drain current based on a change in gate source voltage. Well, in mathematics, that's a derivative. I'm looking for the change of one variable with respect to the change of a second variable. So I'm not going to teach you calculus here, but I'll just show you what the results are. All right, so what I'm essentially doing is I'm taking the derivative of this with respect to the gate source voltage. So when I do that, I get the change in the drain current, which is AC drain current change, divided by the change in the gate source voltage. And that is equal to, this is a constant, so it stays. When I take the derivative of something squared, it gets complicated, but what I get is the 2 comes down. The original inside the parentheses stays, but its power becomes -1. So 2 minus 1 is 1, so I just get that to the first power. But then the chain rule requires that I also take the derivative of what is inside. Well, 1 is a constant. So when you take the derivative of something that doesn't change, you get 0. The derivative of this, right, I'm taking the derivative of, or with respect to the gate source voltage, so this basically produces -1 over the gate source cutoff voltage. That's the derivative. All right, Larry? You teach this stuff, right? So I'm going to define this as the transconductance. But we call this the transconductance curve. In this form, it relates the DC value. In this form, it relates the AC values of the drain current and the gate source voltage. So this transconductance is basically going to relate these two things. So if I were to actually solve for the drain current, using this part right here, the AC drain current would be the transconductance times the AC gate source voltage. That's my current. That is my current source. That is the transconductance times the AC gate source voltage. That's the value of that current source. But let's go ahead and finish all of this. So I actually look at the transconductance here. We have IDSS times 2 times -1, so that'll be -2 times IDSS divided by the gate source cutoff voltage. That's the negative coming out there. There's your 2, there's your IDSS, and there's that. Times 1 minus the gate source voltage divided by the gate source cutoff voltage. Taking a derivative, what this formula actually gives me is the slope of this curve. That's what it gives me, the slope. Now, if I were to graph this, this will be the transconductance versus the gate source voltage. So similar to what I did here, right? When the gate source voltage is the gate source cutoff voltage, those two are equal. Anything divided by itself is 1. 1 minus 1 is 0. And the transconductance at this point would be 0. That's at the negative gate source cutoff voltage. The gate source voltage is 0. I have 1 minus 0, which is 1 times that. That point is defined as the transconductance at 0 gate source voltage. You know how do these two connect? Oh, by the way, that number is equal to this part right here. That is what I'm going to call a transconductance at 0, right? And that is 1. So that is defined as -2 times IDSS divided by the gate source cutoff voltage. And how are these related? Well, it is a negative slope, but now there's no square. It's linear, just a straight line. Now, the neat thing about this is something that's a little bit easier to actually figure out what that transconductance at 0 is if you want it, right? There's a set slope there. So this formula, if you get enough information, and a lot of times I give you a gate source cutoff voltage, I give you a IDSS, you had one earlier, right? The transistor that I had earlier, you wanted to calculate the transconductance at 0, it would be -2. My IDSS was 10 milliamps. The gate source cutoff voltage was -3. That's focus. What are the units of conductance? Bose is an older, they've renamed it since I was in school even. It is now the Siemen, SIEMAN, I think, something like that. Right? So negative divided by negative cancels out. 2/3 of 10 would be 6.67 milli Siemens, right? Amps divided by volts is a Siemen. The mho that Larry was talking about is the upside down omega because it's the opposite of resistance. That's older text, you may see that. This one uses the Siemen. So if I know where I'm operating on this curve, right? If I go and measure my gate source voltage, and I roughly know my gate source cutoff voltage, I can now use this here and calculate what my transconductance is. Once I know the transconductance, I have that piece of information. So this becomes my AC model for my junction field effect transistor. And a lot of times, in terms of hooking up your, if you were to hook up the transistor and bias it with a gate source voltage of 0, put a signal in, and work backwards to how much of a gain you have, you can actually provide a pretty good estimate of the transconductance at zero. We'll see that here in a second. And so if I solve for IDSS, I'm sorry, no. If I solve for the gate source cutoff voltage, just basically swap that, it'd just be -2 times IDSS divided by the transconductance at zero. So this is actually another way this could be found, because IDSS is really easy to find. You're going to do that in your lab. Just hook up a meter, make the gate source voltage 0, provide a voltage, boom, there's IDSS. Done. Transconductance is 0. We'll show you a way to do that here. Well, sometimes use them. All right. So let's take this model now and go ahead and put it into a circuit and figure out how the circuit's going to operate. What kind of expectations do we get in terms of voltage gain, etc. Here's your amp. Again, voltage divider bias, there's multiple methods we can bias into our active region. Then we add a coupling capacitor. We're going to assume a generator resistance. Well, now we have a gate, so maybe that's not the best symbol to use. Maybe we won't worry about it. Oops. Yeah, he doesn't, so I'm not going to. All right. We have an input coupling capacitor. We bring that in. We're going to, of course, have a output coupling capacitor to a load resistor. Now, one of the things that I also need to have happen here is just like in a common emitter amplifier, this is a common source amplifier. So I'm going to add in a source bypass capacitor. To AC, that will make the source ground, thus keeping the source constant and allowing whatever signal I put in onto the gate to make that gate source voltage change. So when we draw our equivalent circuit, we have our generator voltage coming in. Capacitor will once again act like a short. And I will simply go right to the model, the gate to source resistance. And if you recall from the model, that's the source, which because of the source bypass capacitor, acts like that. And then on the drain side, we have our transconductance times our AC gate source voltage. Again, the source goes to ground. The drain is connected to the drain resistor, which goes to AC ground. You know what? I missed a few things here. I forgot R1 and R2. So let me go ahead and add in R1 and R2, right? So I have R1 goes to a set DC voltage, which acts like AC ground. R2 does go to ground. Okay. And then over here, I have my drain resistor, again, going to AC ground. The output coupling capacitor acts like a short, and now I have the load resistor also connected to that point, going to ground.
It's the same.
Looks almost the same. Exactly. All right. But not quite. because this current source has a different nomenclature. So this, of course, is my input voltage, and I'm looking for my output voltage. Well, remember, this is the gate. That's my source. So the input voltage is the gate source AC voltage. They're the same. If I did have a generator resistance, it might be reduced, right? The whole voltage divider loading effect. But keep in mind, because R1 and R2 dividing my voltage do not have to supply any current, these resistors can be huge. Hundreds of kilo ohms, mega ohms even. This is a reverse bias PN junction. RGS is huge, which means the input impedance of this circuit is large. And so any dividing effect from generator resistance, like your generators are 100 ohms, you're not going to notice. No difference. Now, what is the output voltage? Well, this is my drain current, AC drain current. These two resistors are in parallel. We call that the AC drain resistance. It is just the parallel combination of the drain resistor and the load resistor. Looking familiar still, right? It's because it is. Now, that drain current, notice the direction of flow, right? So if I assume that direction and this polarity, that's going to result in this direction of current, and as the current flows into ground and out, creates this polarity, which is the opposite, which means this amplifier does what to my signal? Larry? It inverts it. Exactly. So this is an inverting amplifier. All right, it's an inverting amplifier. And the magnitude of that voltage will simply be whatever the drain current is times those two resistors in parallel, which is my AC drain resistor. What is that drain current? Well, it is equal to the transconductance times the AC gate source voltage, and then times the drain resistance. So the voltage gain for this circuit, output, divided by input, will be this output voltage here, transconductance, times the gate source, AC gate source voltage times AC drain resistance, divided by the input voltage, which is the AC gate source voltage. These two cancel out. And your final formula for the voltage gain is the transconductance times the AC drain. Just like we've done with other amplifiers, input impedance. It would normally be R1 in parallel with R2 in parallel with RDS, but because RGS is so big, the author just says, you know, I'll put it approximately there. It's basically R1 in parallel with R2. The input impedance of the transistor itself is huge. So just those resistors. And we can make those resistors fairly large, which means we have a fairly high input impedance for this amplifier. What's the output impedance? Looking back in from the perspective of the load resistor, current source gets replaced by an open, and all we see is the drain resistor. Questions? And follow up for the finish calculations here. Go ahead and put some numbers on here. We'll make our drain resistor here a 2.2K. And let's say that we bias this and we know that the gate source voltage is -1 volt. Now, based on that, the transconductance before my, so again, we're using the same transistor, 10 milliamps for IDSS, gate source cutoff voltage, -3 volts. So the transconductance at 0, we calculated over there, 6.67 millisiemens. And then that'll be multiplied by 1 minus the gate source voltage, -1, divided by the gate source cutoff voltage, -3. So -1 over -3 is 1/3. 1 minus 1/3 is 2/3. So 2/3 of 6.6666, lots of sixes, will be 4.44 millisiemens. Oh, and my load resistor will make it 10K. Using those numbers, 2.2K in parallel with 10K is 1 point. Is it 1 point? I think it's 1.8K. We double check. 10 times 2.2 divided by 12.2. Yep, 1.8. It's 1.8 kilo ohms. So the voltage gain for this circuit would be 1.8 kilo ohms times 4.44 millisiemens. Remember, ohms is the opposite of Siemens, so those cancel out because voltage gain has no units. So I have 1.8 times 4 point, lots of fours, give me a voltage gain of 8.01. Right, because kilo times milli also cancels out. Make sense to everyone? Question?
About impedance of the stage.
I didn't give you R1 and R2, but let's just say it's we'll say this is 100K and this is 40, say 556K, right? Roughly 1/3. And so that would just be, oops. What impedance then would just be 100K parallel with 56K, 5,600 divided by the sum, which is 156. So about 35.9K. In other words, very large. Any other questions?
Where did the 1.8 K ohms come from?
The 2.2K ohm drain resistor and my 10K load resistor.
Vi var stilla på andemagar. Vi var stilla på andemagar, that's why I got confused.
Okay.
It's getting high enough.
Oh, okay. Move the monitor. Raise your seat. I don't know. All right. So this, of course, is what type? Did I call it back here? I didn't, right? So this, of course, is a common source. Because, of course, the source of the transistor to AC is ground. What else can I do? I also do a common drain. So common drain amp. Just like my common collector amplifier with a bipolar junction transistor, we just remove, in this case, the drain resistor. We still use voltage divider bias. I still want to be in the active region. Because the drain is connected directly to the drain supply voltage, the AC, that's ground, common drain. Signal goes into the gate and comes out at the source. So there's your output coupling capacitor. There's your load resistor. AC equivalent circuit. Again, coupling capacitor acts like a short. R2 and R1 go to AC ground. Now, the transistor, we have our AC equivalent circuit. This time, it's not grounded. What we have coming out of the source, we have the source resistor. This acts like a short. And so the load resistor and the source resistor are both connected to the source, and they both go to ground. Well, we're going to call that our AC source resistance, which is equal to the source resistor in parallel with the load resistor. Drain goes to AC ground. Your drain current, AC drain current, which is essentially going to be exactly the same down here. So the current down here will be the transconductance times the AC gate source voltage. Now here's the tricky part. That is the AC gate source voltage, right? Because here's your source, there's your gate. But the input voltage goes from ground to the gate. Output voltage is across the load resistor, which being in parallel with the source resistor is from the source. Well, we can calculate the output voltage by just taking that current times that resistance, right? Ohm's law. Well, this current is the transconductance times the AC gate source voltage times the AC source resistor. What's the input voltage? A little tricky, but still easy to look at, right? The input voltage goes from here to here. Well, what's between here and there? The output voltage plus the gate source AC voltage. So the input voltage, basically the output voltage plus the AC gate source voltage. Does that make the voltage gain? Well, it's short, not very good, right? In fact, you may remember what, when we do a common collector amplifier, the voltage gain was always going to be what? It was always less than 1. Same thing here. V out over Vn, that's my voltage gain. The output voltage is this. Transconductance times the AC gate source voltage times the AC source resistance divided by the input voltage, which is the AC gate source voltage, plus the output voltage, which is just that again.
So like 1 over the VGS.
Well, if we divide the top and the bottom by the gate source voltage, and we can do that because it's in here, here, and there. But when you do that, your final voltage gain becomes, so basically these all cancel out. What does that cancel to though? 1, right? Because I'm dividing by the gate source voltage. Anything divided by itself is 1. We end up with transconductance times the AC source resistance divided by 1 plus the transconductance times the AC source resistance. So once again, that voltage gain will be less than 1. In fact, common drain, also known as a source follower. We call it a common collector amplifier and emitter follower. Same thing. And as we have done in the past here, right? Your input impedance for this stage, pretty much, again, R1 in parallel with R2. The output impedance. So when I look back in from here into there, I basically see the source resistor to ground. What do I see looking back up into here? Well, looking back that way, I see a current source, so it acts like an open. Looking this way, I have a huge resistance. So we'll just ignore all that and just say, yeah, it's about equal to the source resistor. I don't know if he covers that or not. No, he's got the input. This time he included, nope, simplifies it. Okay, he actually includes the output impedance of the stage is the source resistance in parallel with the input resistance of the source, which, so he adds this in. I'll take his word for it. I'm not gonna quibble. But then 1 over the transconductance. The transconductance, if it's a few millisiemens, means this could be, a few hundred ohms and parallel with that. So it is lower, right? Which you kind of expect, right? Because common collector amplifier, one of its characteristics, low output impedance, high input impedance. You see a lot of equivalence here. Even though the exact operation, the amount of gain that we get is different, there are a lot of equivalents. All right. So that gets us to a good stopping. Okay. The last part of this chapter, which is what I'll finish up with next week, basically goes through and talks a little bit about, all right, how can we use the JFET switching aspects of it, right? Either as a switch, so we're going back and forth between the ohmic region and cutoff, or because it's an ohmic region, what other fun things can we do with that? And that's some of the different things that we'll look at next. All right, so for homework, Oop, wrong one. Ah. So this is week 2. For your homework. Chapter 11. We covered a lot today, so I got a lot of homework for you here. 2, 4, 6, 8, 10, 12. 16. 20, 26. 28. 30. Check this good. Check here. Horsepower. All right. Now for lab, we have experiment number 32. Now, what experiment 32 does for us is basically you explore all those characteristics of the JFET. You measure IDSS. You apply a negative voltage, see what you get. You adjust the negative voltage to the gate until the current drops as low as you can measure to try and find your gate source cutoff voltage. So we're going to explore all that. So that's steps 1 through 8. Then the other part of that is biasing circuits. So you have 3 different active region bias circuits to look at. Just do one of them. So pick one of 3 active bias circuit. So I don't think they have you do. You have it there real quick, Joe. So your choice is self-bias, voltage divider bias, and current source bias. So one of those 3, just one. Right? And then questions will be 1 through 6 as appropriate. So questions 1 through 6 as appropriate. So in other words, if there's a question on voltage divider bias, you did source bias, you don't answer that question. And experiment number 33 is, I don't know what that was. I think it's a JFET amplifier, right? Yeah, it's common. I had to do steps 1 through 6, which I think is just the common source, right? Yeah. So experiment 33, you're going to do steps 1 through 6, which is that common source amplifier. And you'll answer questions 1 through 5 and 6. Next week, we'll move into chapter 12. We'll finish off chapter 11, just a little bit left on that, and then we'll get into chapter 12.
Fifth.
You'll have the kit next week. So I usually have it available next week. That's where you get your JFETs. So you can start doing that. Questions? New stuff today, right? Fun time. All right. That's all I've got. Rest of the time is yours. Work on experiment 30. Right? What happened last week?